Jupiter has a storm on it that's almost 1.5 times larger than our whole planet. It can reach wind speeds of up to 450 miles per hour, and the storm itself is over 350 years old, which is older than the entire existence of the United States. I'm talking, of course, about the Great Red Spot. If we measure that storm from its eastmost end to its westmost end, it would be 10,250 miles across. But wait, how do we know that? How can we measure the size of a storm from a planet that's over 484 million miles away from us? Just traveling there at highway speeds, it would take over 650 years to even get there. Well, to do that, we have to calculate spatial distances. For a storm like the Great Red Spot, it's actually pretty simple to find its size. First, we need to determine its angular size relative to our telescope. So we need to create a triangle with the first vertice being our telescope and the two rays being the east and westmost end of the Great Red Spot. Now, using the formula W equals D times the angle, where W is the width of the Great Red Spot and D is the distance from Earth to Jupiter, and then the angle is obviously the angle that the two rays will make, we can actually determine the Great Red Spot's size. But hold up, how do we even know how far Jupiter is? Okay, now it's getting a little bit complicated, so to make it simpler, we're going to calculate the distance to the sun instead of the distance to Jupiter. The way we actually find the distance of the sun is by using radar, which can actually give us an extremely accurate distance. The way it works is we send radar signals out to a planet like Venus, and then we see how long it takes to get back. Since radar travels at the speed of light and we know the speed of light, we can determine the distance Venus is to us, and then to determine the sun, it's actually just one extra step. See, Johannes Kepler actually created a law of physics that says that the distance a planet is from the sun is proportional to its orbital time. For example, one Earth year is about 365 days, and we know Venus is about 38 million miles away from us, and we know that its year is about 225 days, which is about 72% of our year, meaning its distance is about 72% of our distance. Now, I know that sounds like a lot, so I'll make it very simple. We know the distance to Venus, and that Venus is 72% of the distance from Earth to the sun, so using a simple percentage, we can calculate how far the sun and the Earth are from each other. The beauty of this system is that we can apply it to every single planet in our solar system and calculate not only distances, but also sizes. So now I'm going to give you exactly what you came here for, a real-life scale model of our solar system. If we take the sun's diameter and shrink it to just the size of a basketball, we'll still have a solar system over half a mile long. The sun would be 99.8% the mass of the solar system, and of course the size of the basketball. Mercury, the smallest planet, would be about 0.8 millimeters across, or about the size of a small grain of rock, and about 33 feet away from the basketball of the sun. Venus, the most similarly sized planet to Earth, would be a little bit smaller than a 2.2 millimeter BB pellet, and it would be about 62 feet away from the sun. Now, Earth, our beautiful planet, would perfectly be a 2.2 millimeter BB pellet, and it would be about 85 feet away from the sun. Mars, being the last terrestrial planet, would be about 1.1 millimeters across, or about the size of a fine grain of rock as well, and it would be about 130 feet away from the sun. To give you a scale of how close the terrestrial planets are to the sun, if the entire solar system was shrunk to 1 foot, all of the terrestrial planets would be within 3/4 of an inch. Jupiter would be the size of a ball pit ball, about 1 inch in diameter, and it would be about 442 feet away from our basketball of the sun. And to give you a scale of its size, it actually makes up 0.1% of the mass of our solar system, with the sun being the 99.8%. Saturn would be a little bit smaller than Jupiter, about the size of a sponge ball, a little bit less than an inch across, and it would be about 815 feet away from the sun. Now, the two farthest planets, Uranus and Neptune, would be so insanely far away, it's kind of hard to comprehend. Uranus would be about 8.8 millimeters across, or about the size of a dice, and at this scale, about 1,632 feet away from the sun, or about 0.3 miles. To even get to Neptune would take so long. To give you an idea of its actual distance, it takes about 165 Earth years to make one revolution around the sun. So the last time it was in the spot it's at right now was 1861, when the Civil War had just started. And once we finally get to Neptune, it would be about 8.5 millimeters in diameter, about the size of a smaller dice, and it would be half a mile away from the basketball of the sun, which is so insanely far for that dice to still be controlled by the gravity of that basketball. Like, Neptune is so far away that its own weather is caused by the heating of its core instead of the actual sun.